Now I'm going to start with unit 5 of H51, that is vector space. So before learning about the vector space, let us go revise whatever you have learned in groups. So because we need to know about the group under addition, so let us revise what is a group. Before revising the group, so first of all, let us understand what is a binary operation. Okay, so let us understand what is a binary operation. So here I'll talk about the binary operation. So binary operation. So this binary operation I'll donate with star. So star is our binary operation. Okay, so I'm taking the binary operation to be nothing but star. So star is the binary operation. So star is defined. We have a mapping from the set A cross A. It is sent to A, defined as star is defined to be, I take one element from here, so A, I take another element from A, so this is defined to be A star B, and I have to show this element belongs to A for all AB belongs to A. So if we can show this, then it is binary. So star is a binary operation if it satisfies this. And one more thing, we have to know that A should be a non-empty set. Okay, A should be a non-empty set. So I'm taking here, let me take one example. So I'm taking A to be set of natural numbers, and star I'm donating as plus. So I'll define this plus from the set of natural numbers to natural number, define as take plus. So I'm taking one element from here, so A, B, and this I'll define to be equal to A plus B belongs to, I have to show this one belongs to natural number for all AB belongs to natural number. Okay, AB belongs to natural number. So we know this, we know sum of two natural number, sum of two natural number is always a natural number, is a natural number. Okay, sum of two natural number is a natural number. Now I'm taking, and let me take an element from natural number. A I took from natural number, B also I'll take from natural number. Then what we have by this statement, we know that A plus B is also a natural number. So we have shown that it is a natural number. So that shows that plus is a binary operation. So plus is a binary operation. It's a binary operation. Okay, so we got here plus is a binary operation. Let me take another example. So I'll take A equal to natural number, and star I take as minus. So minus from here, so I take here natural number cross natural number. So here I define as natural number, define as okay, so minus A comma B. I'm taking two elements from here, so this defined to be A minus B for all AB belongs to natural number. So let me take this. I'm taking here A equal to 2. 2 is a natural number. I take B equal to 3. This is also a natural number, but A minus B, let us find. So that is 2 minus 3, which is minus 1. So minus 1 is not a natural number. So this does not belong to natural number. So I got one example of natural numbers. If I take A and B is natural number, but the difference is not a natural number. So therefore, minus is not a binary operation. It's not a binary operation. So we have shown it's not a binary operation. So we want to define about, we should understand about the group also, because in vector space we need to prove it is a group first of all. So let us go through about the definition of groups. So let G be a non-empty set. So I'm taking G to be a non-empty set. I'm taking non-empty set, and star be a binary operation. So I've already donated star to be a binary operation. Is there be a binary operation? Okay, binary operation. Then G is said to be a group. Okay, is said to be a group. If it satisfies the following condition. If it satisfies the following condition. If it satisfies the following condition. Okay. So the first condition is that ester is associative. That is, A ester B ester B ester C is equal to A ester B ester C for all ABC belongs to G. Next, you have to show every element means there exists an identity element. Okay, so we have to show that there exists an identity element. So if I take E is my identity element, then A ester E is equal to A, which is equal to E ester A for all A belongs to G, and this identity element should also be in G. 3. Okay, 3 is every element should have an inverse. So if I take B is the inverse of A, then A is to B is equal to identity, which is equal to B is to A for all AB belongs to G. So every element should have an inverse. If they satisfy this three condition, then we say it is a group. So let us take some example of a group. So I'll take here G equal to natural number, and ester I'll take as plus. So we know G is non-empty, natural number is non-empty, and ester is a plus. So plus is, we have already shown plus is a binary operation, and we also know that plus is associative. Okay, we know that plus is associative because we know that addition of natural number is always associative. So plus is associative. Now let us look that it has an identity element or not. Since the operation is by plus, so let us check we have the identity element or not. So we have A plus E equal to A. We have this condition. So from here we can get E to be 0, but this 0 does not belongs to natural number. So it shows that it does not have an additive identity. Since it does not have an additive identity, this said G plus is not a group. It's not a group. Okay, so it is not a group. Next, we can see here, I'll take another set, G equal to integers. Okay, G I'm taking integer, ester I'm taking as plus. Okay, ester I'll take as plus. So integer is not empty, and is addition of two integers is always an integer. Okay, and also first property says it is true, addition of integer is associative, so it is associative. So it is associative. Number 2, let us check it have an identity element or not. A plus E equal to A, so this implies E is 0, and 0 belongs to integers, so it have an identity element. Now let us check it has the inverse or not. Suppose I take, in general I'm taking an arbitrary element A, and let me think as B is my identity, B is the inverse of A, so this should be equal to identity. So identity we got as 0, so what is B? B is minus A. So this minus A always belongs to integer. Okay, this minus A belongs to integer. So that shows that every element of G has an inverse. So therefore G plus is a group under addition. Okay, so it form a group under addition. Now we'll talk about the binary. We'll talk about the abelian group. Okay, so we are talking about the abelian group. Okay, so abelian group. Okay, a group G is said to be abelian. Okay, a group G is said to be abelian. Is said to be abelian. Abelian group said to be an abelian is said to be an abelian group if A star B is equal to B star A. Okay, if A star B is equal to B star A for all AB belongs to G. Okay, for all AB belongs to G. So now in the example we have checked already, G equal to Z and star I have donated taken as plus. This I have already showed that it is a group. It's a group. Now let us check that it is an abelian group or not. If I take two elements in G, then A plus B is always equal to B plus A. We know that. Okay, addition of two integers is always commutative. So for all AB belongs to G. So A plus B is equal to B plus A. That shows that G plus is an abelian group. Is an abelian group under addition. Okay, so it's an abelian group under addition. So in the next video I'll explain you about the vector space.